Chapter 3 is about the graphs of sine and cosine and tangent functions and stuff.
Did you never? No, I did, but it just slipped my mind. Dude, geometry was so hard. I hated proofs. Useless. I had Garcia. She never let go of proofs. Useless.
Okay.
Are we going to have proofs in this series?
We have proofs in trig and precalc.
Yeah.
We
Are
do.
you kidding?
We have like the trig proofs.
Yeah.
The ones that like.
Yeah.
Are those like they want to like drive off the side of the road?
Wait, no, I suck at proofs in geometry.
Okay.
What if you
All right.
never solved it?
So let's try to reel it in and focus here on what we're working on today. So here we're going to be talking about graphing sine and cosine functions. So if we think about the all right, if we remember back to chapter 1, we talked about this concept of a parent function and a transformation.
Thanks, Grace. You're welcome. Coming in clutch. Thanks, Grace. Anytime.
Everybody kind of remember this?
Yes.
And we talked about how we can use then this same information to transform the specific points from a parent function to the points for our new transform function if we want to graph something. So these two ideas are going to be kind of central to what we're going to be doing today. So this is just recall from chapter 1, stuff that we already kind of talked about, but I want to write it down again because we'll use these same two ideas quite frequently here. And that's probably worth just writing them down one more time because most of us probably don't have these things totally memorized for permanence because you're not all math teachers. Grace?
Does that say MC?
That says map.
Oh.
So the map, that's our map to transform a point in a parent function to a point in a transform function. So this is our parent function point, and that would be our transform function point. Okay. So let's look at now some just kind of a big info dump here. So I'm going to make like a little grid for this. And then we'll just kind of talk about these and fill them in. Sounds like Colton's in trouble. Oops. Here's a tip. Don't argue with Miss Yarrow. Okay. So not all of these things we have defined yet, but we'll kind of do that as we're filling things in also. Okay, guys? So we're going to talk about this for sine and for cosine. So those will be the two columns in our table. So those are our two parent functions that we're going to be talking about. So one of the major results in the first or the second chapter was that we had defined sine and cosine in such a way that their domains are now all real numbers, right? We can have negative angle as small as you want, positive angle as big as you want, like all angles of any size are now defined. Everybody's okay with that idea? So for both sine and cosine, the domain is just going to be all real numbers. Everybody's good with that? Right? When we redefine sine and cosine and took them outside of the right triangle and embedded them as points on a unit circle, we picked that up. Now let's think about the range for sine and cosine. So remember that the outputs, the y values for a sine or cosine function, the inputs are going to be coordinate, or is going to be an angle value, right? Everybody's okay with that? We do sine of an angle. And the output is going to be the y coordinate for that point on the unit circle. So all points on the unit circle correspond to values for sine and cosine, right? So the range for sine is going to be the smallest y coordinate on the unit circle all the way up to the biggest y coordinate on the unit circle. So the smallest is -1 and the biggest is +1. Everybody's okay with that? Cosine is the x coordinate on the unit circle. So the range for cosine is going to be the smallest x coordinate, -1, to the biggest x coordinate, +1. So let's record that information. Notice here that I'm using a bracket rather than a parenthesis because sine and cosine actually can take on the values of -1 and +1. For example, sine of 90 degrees is +1, or cosine of 180 degrees is -1, etc., etc. So those get brackets there. And we know that since the domain for sine and cosine is all real numbers, and they correspond to points on the unit circle, and there's no like gaps in the unit circle, we know we're going to be continuous everywhere. That if I draw this graph of sine or cosine, it's going to be everywhere continuous. So what is the graph of sine or cosine going to look like? Let's do that real quick and talk about where this is coming from. So the graph of sine is going to look like this wave pattern. Let's do that. A little less busy. Y. Remember, the points that we're plotting are just values from the unit circle. So let's just kind of show you what's going on here. So this was sine. if I take the unit circle, let's grab that and drop that in here also. So for example, if I take the point here 0 radians, has the sine value of 0, so that's the point 0, 0. For example, if I take pi over 2 radians, that's my x-coordinate, and the sine output at that is 1. So I have the point pi over 2, 1. If I take pi, the output of that is 0, so there's pi 0. If I take 3 pi over 2, the sine output there is -1. And I'm just kind of connecting things. You know, I could plot more points. I can pull any point from the unit circle, and it creates a point on my graph. But that's basically all I'm doing, is just plotting an angle measure with its value for sine on there. Is that okay with, you kind of see where the graph is coming from? And I can keep going around and around the unit circle as many times as I want. It's just going to be bigger angles, but it's going to be the same y coordinates over and over and over again, right? Okay. So that's kind of what's going on here. If I look at this graph, I notice that this is, the symmetry for this graph is the odd symmetry, right? Where like this core, like those two quadrants look identical. You guys see that? That was odd symmetry. The midline is like the imaginary line that's going to divide this graph. So there's like an equal area above the midline and an equal area below the midline. For y equals sine x, that midline is just the x-axis, right? So like the area above the x-axis and bounded by the curve is the same as the area below the x-axis bounded by the curve. Do you guys see that? Basically, there's the same amount of graph above and below. So the midline, oh, shoot. That was, I put that in the wrong spot. Okay. The midline is the distance from a maximum or minimum back to the midline. So in this case, that distance is going to just be 1, right? Everybody's okay with that? So if we look at this graph of sine, we notice that this graph kind of repeats itself over and over and over again. I'm going to get rid of some of these markings I put on here. So for example, starting here, I have an up hump and a down hump, and then it starts over again with another up hump and down hump. Everybody kind of see that? And it's just going to repeat itself over and over and over again. When you have a graph that repeats itself like this, we call it periodic. And the length of one of those non-repeating segments is called a period. So for example, like this blue section is 1 period. And the length there, if we're going from 0 to 2 pi, how long is that? 2 pi, right? Everybody's okay? So my period is 2 pi. Yes, Allie.
What'd you put for midline?
Y equals 0, and then in parentheses I wrote the x-axis.
Oh.
because they're the same thing, right? We'll use those two terms interchangeably. And then the frequency is basically talking about how many periods you have per 1 unit, like 1 unit length. So the frequency is basically just by definition going to be the reciprocal of a period. Everybody's okay with that? Okay. Let's look at cosine then. Let's get you out of here. So notice if I look at the cosine graph, looks pretty similar, right? But if we compare them at the same time, you notice that they are not identical. Everybody see the difference there, that they're shifted? So again, if I'm plotting this time instead of looking at the x coordinates, or I'm sorry, instead of looking at the y coordinates, I'm looking at the x's. So I'd plot 0, 1, and then pi over 2, 0, and then pi negative 1, 3 over pi, 0, etc., etc. Everybody's cool with how the unit circle is still just giving me the points to plot for cosine? Okay. If I look at the graph of cosine, I notice that it's like a mirror reflection of itself across the y-axis. That's the definition of even, or that was another way of defining an even function. And just like for the sine graph, the midline for cosine is still going to be the x-axis. Everybody's cool there? The amplitude, still 1. The period, let's see, we're going to go from 0 at a maximum to another maximum there at 2 pi. So again, the period is also 2 pi. So the frequency is going to be just the reciprocal. Okay, feel okay with kind of what these terms mean? That's good. Okay. All right. So in general, if our parent function is y equals sine or y equals cosine, our transformed function, and I guess we should call these f of x's, is going to be these, which is just the same thing as the general transform function we gave you at the beginning, except here instead of being a general f of x, we're specifically talking either about sine or cosine, right? And any function that's built around sine or cosine, we refer to as just a sinusoid. So a sinusoid is just going to be a sine or cosine function, any transformation of. Let's see. Let me, make some space because I'm just going to add to this, I think. Oh. There it was. Okay. Oh, do I really want to do that? Yeah. I take it back. All right, we'll just do it here. Okay, so the domain here for any sinusoid can a transformation affect the domain? No, right? Because all we can do with the transformation, we can stretch it vertically or horizontally, we can flip it, or we can shift it left or right. None of those things are going to affect the domain, right? If we had infinitely many x's we could put in, there's no way we can like lose an x value that we could put in by doing something like that, right? The graph is never going to tear and create a hole in it or something by doing any kind of one of those transformations. Does that make sense? So the domain is still going to be all real numbers because sine or cosine's domain was all real numbers. Can the range change? Yes, right? What two components are going to change the range? K and A, right? If we stretch it and it gets taller, or if we squish it and it gets shorter, that's going to change the values of the relative max and mins, right? Also, and it's going to change that multiplicatively. Everybody agree? And then if we have a K, that's going to move it up or down. That'll change those values of the maxes and mins also, but it'll change it additively. So my range here is going to be K minus the absolute value of A to K plus the absolute value of A. Before it was -1 to +1, but after a transformation, we'll multiply that y coordinate by A and add K to it. Everybody's okay with that idea? So the minimum from -1 now becomes -A, and then we add the K to it. The maximum was +1, we multiply by A and add K. And we're going to put the absolute values around the A just in case the A was negative, right? That's not going to affect the maxes and mins. It'll just switch which one was which, but that doesn't really matter. Okay. Amplitude. Is a transformation going to affect the amplitude? Yes. Which coefficient is going to affect the amplitude? The A, right? Because if we're making the graph taller, the midline is going to stay in the same spot if all we're doing is making it taller, but that's increasing the distance then to the midline. And in fact, the amplitude just becomes the absolute value of A, right? Again, it's multiplicative. If that distance is 1 and it grows by a factor of A or shrinks by a factor of A, it just becomes A when we multiply it, right? If it gets twice as tall, then that distance is twice as much. If it gets half as tall, the distance to the midline is going to be half as much. Midline, is the midline going to change? Maybe, okay. It could, right? Now, if all we're doing is stretching vertically or horizontally, is the midline going to change? No. If we, what else could we do? If we reflect, is that going to change? No. Yes, but if we shift up or down, that will, right? It's still got to be going through the middle of the function, but if the function's shifted up or shifted down, the middle shifted up or down. Everybody's good with that? And the k is additive, so our midline was y equals 0 before, so it would become then y equals k now. Period. Can a transformation change the period? Yes. Okay. Which coefficient is going to change it? C, because it's the stretching horizontally is going to make that distance between the repeated pieces longer or potentially shorter if we're compressing, right? And that factor of C is multiplicative. So my period is 2 pi times C. And really, we should probably say the absolute value of C. Again, a period is a length, so it can't be negative. If C was negative, like, that doesn't matter at all. That's why the absolute value is stuck there. Everybody's okay with that? And then the frequency then obviously changed if the period did, because they are reciprocals. Okay. Feel okay here? Okay. So let's do a couple of examples now where we're just going to practice using this big info dump we've had. We haven't really developed any techniques yet, right? This is all just kind of factual information. So let's say our parent function here is, bless you, is sine. And let's say that we have a couple of transformations. Oops. And we'll describe a bunch of stuff about these. Okay, let's start by just listing the values for A, C, H, and K here. So remember, when we talk about this, I'm just going to kind of use that general form for a transformation to identify those. In this case, the a should be -4. The c should be 1/2. Everybody's okay with the 1/2? Okay. The h should be 0. Good. And the k should be 1. So in this case, if I go back to the chapter 1 stuff, we have no reflection across the y because the c is positive. We have a horizontal shrink because the magnitude of c is less than 1. We have a reflection across the x-axis because the a is negative. We have a vertical stretch because the magnitude of a is greater than 1. We have no horizontal translation because h is 0. But we do have a vertical translation, up 1 unit because k is positive 1. Right, you guys remember that stuff? I'm not going to write that stuff all down again because, oh, good Lord, there's a lot of writing, you know? And I'm just not feeling it right now. We'll just say it. That was hard enough. What I'm more interested in here is doing like the domain, the range, the amplitude, the midline, that kind of, the new stuff. So what's the domain going to be? Yeah, just all real numbers again, right? We identified earlier that that domain isn't going to change. How about the range? What's the range going to be? So it's going to be k minus the absolute value of a to k plus the absolute value of a. So that would be 1 minus 4 to 1 plus 4. So that would be -3 to 5. Everybody's okay there? Okay. How about the amplitude? What's the amplitude going to be? That's the absolute value of a. So in this case, that's just 4. Everybody's okay with that? The midline is going to be what? Well, the midline's y equals k. So in this case, it's y equals 1. What's the period? Two pi times the absolute value of c. So in this case, the period is pi. And then the frequency is obviously going to be just the reciprocal of the period, so 1 over pi. Do you guys feel okay on that? Let's just look at the picture here real quick and observe kind of what's going on. So here's sine. That's the green one. And then here we'll do y equals -4 times sine of 2x plus 1. So this should look stretched vertically, compressed horizontally, and then shifted up 1 unit, right? So if I look at the period, starting here, going to there, looks like to be about pi, right? So that matches up. and it's definitely gotten way taller. If I was looking for the midline, looks like it comes in right through here at like y equals 1. So that seems to match up with everything we're saying, right? And just as an aside here, notice that when we're graphing, the x-coordinates, the angle values we're using have been in radians each of these times. That's pretty standard. The reason really we prefer radians to degrees when we're graphing is just because of the scales involved. It's a lot easier to go from like 0 to a little bit more than 6, which is 2 pi, rather than going 0 to 360. That's a heck of a lot of tick marks. So typically we prefer to do that. Okay. Do we feel okay about just pulling those values from the function like that? No big deal, right? Okay. Hold on one second. I want to before. Okay. So that's in worksheet. Okay. And then the problem set. Okay, that's fine. Okay, so let's do this next. Let's actually graph this thing by hand. So when we graph either a sine or cosine function by hand, we're going to start with the key points. So for sine, those key points are and for cosine, those key points are these are something that I would provide to you. I wouldn't expect you to have these things memorized, but they're literally just from the unit circle. They're just the quadrantal angles. So the ones that lie on the quadrant. So 0, pi over 2, pi, 3 pi over 2, and then 2 pi is back again here at 0. So if you're ever like, what are those again? And you don't want to look them up, if you have your unit circle handy, you can pull those same key points from your unit circle. Okay, so let's do an example here of doing this now. So let's say we want to graph, oops. So the first thing that I would want to do is I'd want to identify my values for A, C, H, and K. But that's not going to be as easy as it looks at first here. Why is there a little bit of a complication on this? Yeah, so remember the leading coefficient on our x has to be 1. So we'd want to start by initially factoring that 2/3 off. So when I take 2/3 and I divide it by, I'm sorry, take -2 and I divide it by 2/3, what do we get? Should be something we can do in our heads, right? Dividing fractions is the same as multiplying by a reciprocal. So just 2 times 3/2. Just 3. Everybody's okay? I know that's kind of crummy, but real important. So far, so good. Okay. So now, everybody caught why the c is 3/2. The c is going to always be the reciprocal of that coefficient, because remember that it's 1/c. So 2/3 has to equal 1/c. So if I flip both of them, I'd have 3/2 would equal c. Okay. So I'll make my map then. So I have c times x plus h, a times y plus k. And because this is the sine function, I'm going to use these key points. And Mr. Gulick picked a bad example. He made up a bad example here. Because you can't really add the pi's and the 3's, right? So just kind of a pain in the tuchus. We all okay with what I did there? I think I did all that arithmetic right in my head. And from here, we just plot our points and kind of draw our graph. I'm going to skip that part, though, because I picked a bad example, and plotting this would be something I would say is unreasonable to expect you to do the pi's plus 3's. Yep. I mean, you could just, at that point, I would just turn everything into a decimal to approximate it. But that seems like more work than it's worth to plot some points for you guys to get the idea. Because we did the hard parts already. You know what I mean? From here, just plotting and drawing. Which is not a big deal. You guys want to do another one? Okay. Yeah, of course. All right. So let's say our parent function this time is cosine. I guess we don't really need to even say that. Here, I'll pick one that'll be easier for us to graph. Okay, just like before, first thing that I'd want to do is to factor that 2 out. Everybody's okay with what I did there? So 1/8 divided by 2 is the same thing as 1/8 multiplied by a half. That's how I got the 16. Again, if you have to write stuff like that down or use your calculator, no big deal. I'm just, going to say what I did instead of write it down. But that's okay, right? So A is -2, C is 1/2, H is pi over 16, and K is 1. So when I make my map, I have 1/2 x plus pi over 16, then -2y plus 1. Since it's cosine, I'm going to be using these key points. Again, I don't expect you guys to have those memorized. I have them memorized because I'm a math teacher and I've done this, hundreds of times. So it's, you got to memorize by now. I wouldn't expect you guys to have them memorized. You can always just pull them from your notes or pull them from the unit circle. No big deal. So here, let's see. That becomes pi over 16 and then -1. This one becomes, let's see, pi over 4 plus pi over 16. I think that's 5 pi over 16, comma 1. I'm just adding some fractions there. Half a pi plus 16 pi is going to be 9 pi over 16, and then 3. And then 3/4 pi plus 16 is going to be 13 pi over 16, and then 1. Oops, I said 1. And then that would be pi plus 16 will be 17 pi over 16, and then back to -1. Everybody's okay there? Again, I'm making my, if doing the fractions arithmetic seems hard, again, you can just do it with your calculator, leave the pi's off, do the fraction arithmetic on your calculator, and then put the pi back in. And your calculator can handle the fractions and give you a fraction back. You know what I mean? Okay. So at this point, we've talked about the sine and cosine functions and their transformations. We've talked about how to describe a transformation in words using the values for a, c, h, and k. We've talked about how to graph a transformation by transforming the points. What I want to do now is talk about how we go from a graph or a description back to the function. John.
If there's like we have to graph like a sinusoid wave, we have to write out all the points, or we kind of like all the coordinates, and rather we kind of do it by
So here's what I would say, John, on a question like that. It would depend a little bit on what the directions ask, if it wants a table or not. If it doesn't specify that you need a table, I would just say that these points here, when I look at your grid, there should be like a dot where that point is, and it should be in the right place, and then the line going through it. It shouldn't be just the line.
Yeah.
I should see the points where the points go.
Okay.
At minimum, depending on what the directions say, you might also want them listed. Does that feel okay? Yes, Reese. Of course. And your name's not Reese, it's Grace.
Oh, you said my name?
Did
Yeah,
I?
I thought you said Grace.
Yeah.
Oh, did I
It's
say?
kinda like a-
Maybe I said the right name and thought the wrong name, and somehow
kinda
everything
sounded
worked
like-
out. Well, the masks really kill me, right? It's like, you have similar hair colors and, sit in the same row. I don't know. I don't have a good excuse. It's all a bunch of crap. Okay, so let's do a graph to equation first, and then we'll do a description to equation after that. Sound okay to you guys? I mean, you don't really care. You're going to do whatever I ask you to, right? You're just like, whatever, Mr. Kulik, you're in charge. Oh my goodness, that is teeny tiny. Ugh. Make my own. Whoa, excuse you. Ha 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 ha. There we go. Actually, I think I want the grid here. Yeah. That'll make life a little bit easier to have that grid in there. Okay. So, let's say I want to write a sine or cosine function for this graph. Everybody's okay with that plan? Okay. So I need to then come up with, we'll do it both ways just for fun. Okay. So what I like to do to start is identify the midline. So if I look at the graph, it appears that this would be my midline. You guys agree with that? So what does the midline tell me? It tells me the value for k. Everybody good with that? The next thing I'm going to do is figure out the amplitude. That's just going to be the distance from there to there. What's that going to be? 3. Everybody's good with that? Just counting. right? Going from 2 to -1 was 3 units. Everybody's happy with that? So next thing I'm going to do is count, or is going to try to figure out the period. So I'm going to say, let's go from, say, oops. This minimum to this minimum is 1 period. Why am I interested in the period? Because it's going to give me C, right? John? Sure. So if I look at this, I'm going from a little bit more than 1/8 of pi, right? This right here would be 1/8 of pi. Over to here, which is a little bit more than 1/8 of pi, or sorry, 1 1/8 of pi. Everybody see that? So how long is that? Pi. Everybody's okay? I went from 1/8 to 1 1/8. So that's 1 unit that I traveled. And since I know that this is going to equal 2 pi times the absolute value of C, I know the absolute value of C is 1/2. So far, so good? Okay. Boy, did I pick something stupid or what here? I really want to know how far that is. Guess I probably would have given that to you, huh? Yeah. Okay. So there's that. So we have a C, a K, and an A. Everybody's okay with how we've done that? Now keep in mind, I don't know A explicitly. I know the absolute value of A. So that means A could be +1 or -1. Same thing with C. C could be +1/2 or -1/2. Everybody's so far so good? So we really have the freedom to be able to choose either one, but depending on our choices here, it'll affect the H. Everybody's okay with that? Now, for me personally, I always pick C to be positive. I don't find that I've ever run into a situation where picking C to be negative makes the problem easier. So that's just my way I like to do it, but I want to be clear that it doesn't really matter. Everybody's okay there? All right. Now for sine, I know in the parent function of sine, I have the point 0, 0 that's a point on the midline, right? Okay. So let me do this. On the parent function, we go from a min to a midline point to a max. When I look at the points in the key points for sine, so I have a midline, or I have a max, a midline, then a min, or I have, oh shoot, hold on. Yeah, all right. So Okay, let me rephrase. This will be the... So I want to be able to use this point to figure out my h. I'll show you why in a second, why that point is the easiest. It really has to do because the x-coordinate is 0. It makes life much easier if the x-coordinate from your parent function is 0. So the point before would have been a minimum, and the point afterwards would be a maximum, and that's a midline point. Everybody's okay there? So I'm going to go look at my graph now, and I'm going to find a midline point where the same thing is happening. I would choose this one here because I have a minimum, my midline point, and then a maximum that matches up. If you pick them so they're in the other order, then the a has to be negative. If you pick them in the same order like this, the a can stay positive, which is what I'd like to do. So let's write that down. What is 3 was what it was, right? So that is the point 0, 0. And I want to be sending this to the point, let's see, that is a half plus a third more is what that looks like. No, that's a quarter plus a sixth. So a quarter plus a sixth would be, oh my God, 5/12, I think. Alyssa.
Can you explain the top part of it, the main, like what the purpose those lines?
Yes. Okay. Totally fair question because I've kind of stumbled through this, right? Because I know what I'm doing. I'm just having a hard time verbalizing it. So what I want to do is, because I've chosen my c to be a half, I've chose my c to be positive and my a to be positive. The landmarks, the features in my parent function have to be the same order of features in my transformed function. So in my parent function, if I'm using that point 0, 0, immediately preceding 0, 0 would have been a minimum. 0, 0 is on the midline, and then I'd have a maximum after it. So if that's the case, when I choose a point to use in my transformed function, like I chose to use this point here, this point here, I chose it because a minimum precedes it and a maximum follows it. So it's the same landmark order as my parent function. If I wanted my a to be negative, I could have picked them in the opposite order, where it goes max, midline, min. Because then it would be like you're flipping it, so everything is fine. Does that?
Yep.
Okay. Okay. And this is the key, is I know here that xy goes to cx plus h, ay plus k. All I really care about is the x-coordinates. So 0 is equal to 1/2 times 0 plus h. Oh, my goodness. Sorry. This is equal to 5/12 pi. Excuse me. So this is equal to this. Or that is that x.
Why are we only doing X? It's just,
Okay, the reason is because we're trying to find H. The whole thing is we're trying to find H.
H, gotcha.
So I don't care what's going on with the Y coordinate because I've already figured out the A and I've already figured out the K.
Gotcha.
So it does not matter.
Perfect.
And the reason I'm choosing 0, 0 was the point I had such a big deal I wanted to use that one is because the C value doesn't matter. Whether C was positive or negative, didn't matter to me. The H is still going to be the same. So it kind of helps like insulate me from making a mistake. Because if I'm using 0, 0, the X coordinate that I'm multiplying the C by is 0. No? You look confused.
Sure.
Oh my goodness. We'll do more practice. This will get easier. I'm having a bad day or something. Taylor.
So with H,
Mm-hmm.
can you go back up to the graph?
Yeah, absolutely.
So I remember seeing once, actually I'm looking at it right now because I looked it up. It's
Okay.
the distance from the y-axis to the first intersection, like at the midline. Does that make sense?
So you're saying that you're just doing this.
Yeah.
Yeah, where this is H and this is K.
I guess in a way.
Yeah.
Yeah.
That's true.
So does that work? Like in general, if you have a graph, you look at it, oh, this is this distance, and there you have it.
Yes, but then you'd have to be careful about your signs for A and C.
Yeah. So like for this one, A is negative, correct?
No, A would be
A
positive
would be positive?
Mhm.
Okay.
because the order of the points preceding that, the point we're translating to is minimum, midline, maximum. If you had instead wanted to do, like here to here, and called that the H and K, then the A would need to be negative
Is this
because it
for-
goes max, midline, min
Is this for cosine or sine?
for sine.
For sine.
Different for cosine,
Okay.
unfortunately. But yes, you can think about it graphically that way. You can literally count and find your H. You have to be careful about your sign for your A afterwards and assume the C is positive. But yes, that would be okay. So we have everything now for our sine function. Let's see what happens for cosine then. So the K stays the same. The amplitude is going to stay the same. The C value is going to stay the same. John.
So, but the C value at the top there is 1/2.
Yeah.
But then
Oh, yeah. Perfect, yes. So that's 1/1/2. Thank you. Thank you. Or 2, right? Thank you. Yes, absolutely. If you catch me doing something stupid, make sure you raise your hand and tell me I'm doing something stupid. Did everybody see what's going on? What John's complaint was? So in the function, in our general transformation, it's 1/C.
Yeah, but then you just
I wrote, right.
Did you write 1/2?
I just wrote 1/2.
Oh,
And he's like,
okay.
that's not the right.
Okay.
He's
I
like,
see
isn't
what
that
you-
wrong? I'm like, oh, yes, it is wrong.
I see what he's got.
So I had to go back and fix that, make it 1 over 1/2, or you could write as 2. In fact, I'd prefer you to write it as 2, but I figured I should write it as 1 over 1/2, so as if you're going back to look at this, you're not like, jiggle, what? Yeah. That's right. Okay. So let's do the cosine one. Let's find this h. So I'm going to do the same thing here. For my parent function, I'm going to use the point 0, 1, which is a maximum. And in my transform function, I want to pick another maximum, which would imply the a has to be positive. Or I could use a minimum if I wanted to, if that's more convenient. But in that case, then the a would have to be negative. Okay with that? So I'm just going to go back to my function here and choose any extreme point, either a max or a min. So let's say we wanted to use this point. Everybody's okay? Since this is a minimum, oh my goodness. OneNote just barfed at me. And that point was, what was that again? That is 1/6 pi and -4. So I can say then that Cx plus h is equal to pi over 6, or just the h is equal to pi over 6. We're going to stop here.